In this presentation, we'll be looking at how X-rays are created. This is a list of the learning outcomes as required by the SACE guidelines. In this slide, we'll talk about an apparatus that creates X-rays. So we start off with a filament that is connected to a low voltage power supply. Now this affects the intensity of the electrons that are emitted from the filament. Around the filament is a hood denoted by the letter H, and this focuses the electrons in one direction. So when the electrons leave the filament, they cross a gap with a high voltage applied across this gap, which accelerates the electrons and gives them energy. Now this voltage supply is in the order of thousands of volts. On the other side of the gap, there is a target. Now this target is made up of copper for its heat transfer properties, and also a hard metal such as tungsten for its high melting temperature and its hardness, because it's going to be bombarded with a lot of electrons. Down from the target there are cooling fins, and this also helps further dissipate the heat that is created. Just a little bit more information on the target material. Now this material was chosen to be hard as the electrons that hit it have high energies, and if it was a softer material you might find that the material becomes corroded or pitted and will need to be replaced frequently, so choosing a hard material is important. In addition to that, most of the energy is transferred to heat, so this heat needs to be dissipated, and having a target material with a high melting point is also important. Now, a lot of the time a material such as tungsten is used, but can also be palladium or silver or another material with a high atomic number, and this makes good for X-ray production and being of that high melting point. In the previous diagram we saw cooling fins used to dissipate the heat from the target. In the diagram below we have another example of how the cooling can be managed. We have a rotating target, which means when the electrons are emitted and they hit the target, it's in a different location every time, and this reduces the heat build-up. This can also be further enhanced by using a coolant of sorts as well. In an X-ray apparatus, when the electrons leave the filament, they travel towards the target. When they hit the target, photons are emitted, and these photons are in the order of X-ray frequencies or energies. Now, having a look at these spectrum, there are three important things that we need to know about them. One is that there's the continuous spectrum, meaning there's a range of frequencies that the photons are emitted. Number two is that, having a look at the diagram on the right, there are sharp spikes, and these spikes are associated with the metal that's chosen, the hard metal of the target. Now, for every tungsten in different X-rays, you'll always have those spikes in the same place because of the material. Now, these sharp spikes will be different in different locations when we're talking about silver or another hard metal, but for each metal it's in the same place. Now, the third characteristic is the maximum frequency. Now this is dependent on the accelerating potential difference. So when the electrons leave, or when the electrons cross that gap, they have a certain amount of energy. Now the maximum frequency of an X-ray emitted has to be equal to the maximum frequency of the electron that's crossing that gap due to the conservation of energy law. Let's have a look now why X-rays are produced at a range of frequencies. So we've got just a simple diagram here. Let's focus on the circles with a plus inside. What these denote are nucleus of the atoms of the target material. Now we've drawn them far apart because, as we know, atoms are comprised mainly of empty space, with the nucleus being central to that, electrons floating around the outside but really far away. So these nucleus are far apart. When we shoot the electrons at the target material, we've got them denoted here on this diagram by the blue paths. So first of all, let's have a look at electron A. Now this electron A is fired at the material, and it just passes straight through as it is equal distance between two nucleus in our structure here. So it just passes straight through. It has forces that are equal from both, so the forces balance, it just passes straight through. Now if we have a look at electron E, it impacts one of the nucleus directly, meaning when the electron hits it, it will stop and all the energy will be transferred into a photon. So that's where we talk about our maximum frequency. That photon that will be emitted will be of equal energy to the electron that came in. However, between those two ranges of 0 and the maximum, we can have other photons that are emitted. So if we have a look at D, for example, this passes close to a nucleus, and by changing its direction, it's actually accelerating. So because it's accelerating, a photon will be emitted. However, this will be at a frequency that's between the 0 and the maximum frequency. And depending on how close this passes to the nucleus, depends on where that is in the range. We can have a look at another case. This diagram has a little bit more detail. We've got 4 electrons denoted by 1, 2, 3, 4 on the left, and they're passing within range of a nucleus. And you can see when they pass closer or further away from it, the energy of the X-ray that's produced varies. Let's have a look at a derivation now that we can use to calculate the maximum frequency of the photons that are produced. So what do we know? We know that the maximum energy of the electrons is dependent on the charge of an electron and the voltage gap that it crosses. So that's this equation here. We also know that the energy of a photon is denoted by this half of the equation, h times f max. And what we can do, we can equate the two, being this equation, and rearrange, and we find that the maximum frequency is dependent on the charge on the electron, the voltage, and Planck's constant. Now we know that the charge on the electron and Planck's constant are constants, so the maximum frequency is solely dependent on the potential difference through that tube.